How fast do you move as an earthling? Well, let's draw a picture. That's usually always helpful. So we've got the sun here. And we've got, let's assume circular orbit. Kepler's first law of planetary motion says that objects orbit in an elliptical shape. Okay. But the planets are nearly circular. So a circle is a type of ellipse. So there's no sort of violation to that law. If the orbit were a perfect circle, it's not exactly perfectly circular, but for our purposes, we'll assume that it is. Okay. So here's the Earth at some time in our orbit, and we know we sort of go around somewhere, right? If Earth at this moment is moving sort of this way, the velocity vector v, okay, tangential to the circular orbit, and all of a sudden there were no gravitational force, then Earth, remember, would go in that direction of Newton's first law, which is to maintain the current state of motion. So the fact that Earth moves in a circle is evidence that there is some centripetal force acting upon it. And that only tells us the direction. So we know that there is a vector, an acceleration vector, and a force vector that are pointing this way towards the center of the circle. And that's what sort of keeps it moving around. The compromise between its inertia, which would have it go tangentially, and the center-seeking force, which would have it move this way, is orbit. Okay, the compromise between them. So this is both the direction of the center-seeking force and acceleration, related by Newton's second law of motion in terms of the centripetal force and centripetal acceleration. So this F equals ma, but these are the center-seeking force and acceleration respectively, going the same direction as well. I kind of see that because we kind of, like I've drawn here, a moment later, the Earth is sort of moving like this, and you could actually subtract these two velocity vectors. Remember, we learned different ways of doing that, subtracting vectors. You can put them tail to tail. Right, so if I translated this vector like here, where would the resultant point towards the center? So by subtracting these two velocity vectors, you see that that's the direction of the acceleration vector, right? And we know that net forces point in the same direction as acceleration. Like that's kind of like the common sense of physics. Like, of course, things accelerate in the direction we apply a force in. Like if I push the calculator this way, it's never going to accelerate that way, right? Like it's kind of like, yeah, push it, goes that way. All right, so we got this. But remember, this is just the direction. It's just it's pointing towards the center. What is the agent of this centripetal force? What's causing it in this situation? So like we have a couple of examples over there of what might cause centripetal forces. Or somebody say gravity. Who came up with a good law of gravity? I'll say Einstein. Hey, Einstein. There's another guy before Einstein that had a pretty good way to think about that. Not the best way to know it, but a pretty good one. His name's on the chalkboard. Newton. Does anybody know Newton's law of universal gravitation? It was also on the chalkboard the other day when we looked at the four fundamental forces. So one of the four fundamental forces is gravity. I said, well, here's really sort of the equation we like. So in this equation, this m is the mass of the planet, okay? The mass of the thing that is sort of going around the circle. Not the mass of the star, which is creating the gravity field, which is really sort of, Einstein does away with this idea of forces, and it's just like it is moving in a straight line. The problem is that space is curved, and so as things move in straight lines in curved spaces, it's inertial. And so Einstein keeps the physics very simple. Things move in a straight line, but he makes the geometry super complicated. Like space-time is curved, and it makes the math really hard. Like the geometry really complicated, but the physics stays simple with Einstein. There's no need for a force like this. You say, well, there's gravity's not really a force pulling things. It's just like massive objects bend space-time. Like this Earth underneath our feet has bent all the space, and things just sort of follow that curvature. They're pulling the curvature of space-time. That's Einstein's idea. very quickly, right? And so because we know this is the force providing the centripetal acceleration, we can set these equal to that. We know that centripetal acceleration is the tangential velocity squared over r, where r is this distance, the radius of the circle. Okay? So we can substitute this in for centripetal acceleration. So then I see anything else that we can do here, sort of mathematically, to clean this up a bit. So anytime you're looking at an equation like that, and you see the same thing on both sides of the equal sign, and they're in the same place like they're both in the numerator, divide by that thing, right? So divide by m on both sides, if we're allowed to do, what's going to happen? Divide by m 1 times the centripetal acceleration is just that. M divided by m over here is 1 times this is just the rest of it. It's like canceling, right? Like this mass cancels. Doesn't matter how massive this thing is. Okay. So we have the centripetal acceleration, which remember is this. So we'll just sort of substitute that in here on the right side. That's v squared over r equal to g mass of the sun over radius squared. The question that I posed to you was what? How fast are we moving? So what do we want to kind of isolate? V, right? The velocity we can solve for. So multiply both sides by r. We got v squared equal to, that r will cancel one of those r's, we get gm over r. How do we isolate v now? Look at v now. What is it? Look at v now. That equal what? The root. This equation right here we call orbital velocity. Orbital velocity. The Earth orbiting the sun, or a space station orbiting the Earth. Okay, the moon orbiting the Earth. Think about how slowly the moon orbits the Earth because it's so far away, compared to the space station, which is much closer to Earth. In fact, in that video, Chris Haskell kind of talks about, like, I always think about how, as you like hit the engine pressures, it's different than flying an airplane on Earth because it's like you're increasing your gravitational potential energy. So you up and towards, you go slower up there, you're further away. Like the closer in, the faster you have to move to maintain that sort of orbit. The further out you are, the slower you are, and that's the orbital velocity. So we can plug in numbers and solve at this point. The mass of the sun, this is the symbol for the sun. It looks like a circle with a diamond on the 3D eyeball. The mass of the sun is 1.989 by 10 to the 30 kilograms. The radius, which is the distance here between the Earth and the sun, the distance of the light that's coming through the window had to travel to get to our eyes. In meters, it is 1.5 by 10 to the 11. So it's 150 million kilometers, or 150 billion meters, right? That's 93 million miles, 93 million miles. Or, physicists, kind of lazy mathematicians, they can't, these are big numbers, can't we just make it like one astronomical unit? Okay, so we have a unit called an astronomical unit that is an Earth-Sun distance. And it's a great way to just sort of compare everything to Earth. Like Earth goes around in 1 year, right? And it takes Pluto 248 Earth years. Okay, so we compare everything to that, instead of dealing with like these numbers. But in order to get the idea of base units, right? So we need everything in sort of the SI units if we're going to get like meters per second. So we'll get meters per second out of this. G has a value of 6.67 by 10 to the negative 11. And if you look kind of at the equation here, we know we got newtons of force. And so the units of G have to be such that we are going to cancel out the meters squared and cancel out the kilograms squared here. So it's Newton meters squared per kilogram squared. So those aren't like the base units, but those are all SI units. Those are the units of G. So if you plug this value into this equation, when you multiply two masses in kilograms, you're gonna, you have kilograms squared here, but because kilograms squared are in the denominator, that's gonna meters squared here, right? Radius is in meters, that's gonna cancel due to this. Like these terms go away, you're left with newtons of force. So newtons of force equal newtons of force. This has the correct unit to do with that. So that's all you need there to calculate how fast you're moving, right? Go. Okay, you got that. All right, now. Anybody else got it yet? Still got it. Let me know you got a number that you feel pretty good about there. Everybody with a calculator who's multiplying this number by this number, dividing by this number, and then raising it to the 1/2 power, or taking the square root, or however you kind of do with that radical there. Just take the square root. Knows what the velocity is? Yeah, that's what I get too. What will we report on the answer? So I was thinking about that. I don't want to run up to 30,000. I think that's the best thing to do. That's about 30,000, right? So it doesn't round down to 29,000. It's like 29,700 something. So let's just say it's about 30,000 meters per second. Okay, that's how fast we're going. But like, well, that seems fast. Let's turn it to miles per hour. Everybody remember how to do that? Multiply it by my birthday. 2.23. Okay, February 23rd. Multiplying meters per second by 2.23 is a magical conversion factor to turn into miles per hour. And so we get 66,000 miles per hour. All right, that's how fast we're moving. Just by virtue of the fact we're on planet Earth. The entire Earth, along with the rest of our solar system, the sun and all the planets, are in orbit around the Milky Way. So our galaxy is like a spiral galaxy that rotates, and it takes us about 250 million years to do one galactic orbit. And we can do a similar calculation to see how fast we're moving by virtue of the fact that our entire star system is sort of moving around the galaxy. Our entire galaxy is moving through intergalactic space, like speeding towards the Andromeda is really the best thing we can kind of use for comparison there. Or there is a bath of radiation that's sort of all around us right now. It's in the microwave range, so we don't see with our eyes, but there is what's called cosmic microwave background, which is sort of the afterglow of the Big Bang. So we can kind of observe the light that was, created at the beginning of the universe still today that sort of reached us now. And it sort of, comes from all directions and It's really one of the strongest lines of evidence that suggests that the Big Bang, theory is correct. Relative to the cosmic microwave background, we can measure our galaxies too. And the speeds just get faster, actually. So like this is, seems very, very fast, but I think when you do the calculation for the galaxy, it's like 500,000 miles per hour. And even faster still when you compare how fast like Andromeda and the Milky Way are barreling towards each other on a collision course to become some super galaxy, Andromeda, in the next 5 billion years or so. Andromeda way, Andromeda. And that's like 2 million miles per hour. Okay, so it's like we don't know. Like it could be that Earth in its orbit is going this way, but at certain times of the year we're moving against the way that our star system is moving around. But certain times of the year we might all be going in the same direction. So you could say, well, everything lined up perfectly, and all these velocity vectors sort of were pointing in the same direction. We're going this plus the 500,000, 500,000, plus the 2 million. Everything happens to be sort of lined up right. But it's possible that like that our certain times of the year, the position of Earth in our orbit is pointing away from the direction the entire star system is moving around, and that could be pointing in a different direction than the entire galaxy. It's hard to answer the question exactly how fast we're moving. Again, Einstein would say it's all relative. Relative to what? I think all of us right now we're not moving at all. We're all stationary relative to like the planet Earth. But the entire Earth right now is moving around the sun pretty quickly, relatively speaking. But this is like we just learned this today. Centrifugal force. So saying, okay, well, some force acts this way, and it's got the gravity, and there's these are the values. Is there another way to get to this answer? I think we could just say our velocity is distance over time. And the time that we take to orbit the sun is 86,400 times 365.25. So you should recognize these numbers as what? Number of days in a year, which is what we know takes the orbit 1 year, accounting for the leap year. Okay. Number of seconds in a day, so that's 86,400 seconds in a day, 365.25 days in a year. What distance do we travel every year? Remember, R is 93 million miles. I actually don't want seconds, I want hours. I want to do miles per hour. So let's do, there's this many days in a year times this many hours in a day. Let's do miles per hour. Okay, so now we'll be like, we know the time is 1 year. 1 year times 365.25 days per year times 24 hours per day. So now we'll be miles per hour. So what's the distance we travel in a year? Don't say 93 million. I'm setting you up for a joke. Okay, this is a devastating orbit. That's a devastating orbit. Our orbit every year is not us crashing into the sun, traveling 93 million miles. It is rather 93 million times 2 pi, right? 2 pi r circumference. Remember, we're assuming a circular orbit. Well, it's an ellipse. Remember, we're not breaking out the math books and looking at like the circumference of an ellipse. We're assuming circular orbit to keep the math nice and simple. So let's just say that this distance is 2 pi 93 million miles per hour, remember? So we forced the denominator to be hours. So now we just, can do that and check this. This just relies on what? Kinematics. No force is needed. We know it takes a year. We know how far away we are. This is a kinematic calculation. This is a dynamics calculation. We're just saying, hey, something is causing this motion, and we can deal with that too. So tell me what you get for this, and see how closely it agrees with this answer. Realize that's tough to see. So this calculation over here is just saying kinematically, velocity is distance, which is the circumference of a circle, 2 pi, and then r is 93 million miles. For the time that it takes us to go that 2 pi 93 million miles is 1 year. So we have 1 year, which is 365.25 days, times 24 hours per day, and then days cancels, or miles per hour. Okay. And then what do you all get for that? I think it rounds actually up to 67,000, like 66,000. Yeah. And again, you can kind of see the significance where you can be like, I want to be very precise with my days, with like 93 million. Like you could look up right now on NASA's website exactly, like almost to the, inch, I think, we got very accurate measurements of this now. So this works out to be about, maybe have that out of your calculator, 66,000 something. So we'll say it's 67,000, I think, if you just put it. So it basically agrees, it's like, oh no, it's wrong, physics broke. I mean, that's so close to the question. So that's kind of cool. I think that's a neat little calculation to do, especially this one, because students begin to learn about circumference kind of earlier on in their academic career. And so that's the kind of calculation you can do with, to kind of pique their interest in business. Like, hey, we can figure out something kind of cool with how fast we're going. Students know what it feels like to go, 55 miles an hour. They can see the scenery moving faster, 70 miles an hour on the interstate or something like that. But then to say, yeah, the whole planet Earth is going this fast. We've never built a spaceship this fast. There are times of the year where, like, we sent some spacecraft out in the 70s called Voyager that are now beyond Pluto's orbit, and we still communicate with those spacecraft. And so back here on Earth, you can see how far away Voyagers are, 1 and 2, in real time. And there are times of the year where the distance between Earth and Voyager is decreasing. And so we'll have, oh, turn around, it's coming back. No, it's because Earth is faster than Voyager. So there are times of the year where Earth is catching back up to Voyager because it's speeding towards Voyager. Voyager can't get away faster than Earth can catch up to it, because that's faster than Voyager. And Voyager is the fastest thing. I think, well, maybe New Horizons is faster, actually. Because New Horizons got out to Pluto in just a couple of years before Voyager. That was kind of why New Horizons was such a neat mission, because we were able to just sort of get there so quickly based on the plans lined up. So New Horizons has since, I don't think it's caught up to the Voyager. It turns out far away there, but it will. But still not as fast as it is. Okay. All right.